In this video, we're going to look at a word problem that involves the ambiguous case of the law of sines. The problem says that the distance from the sun to the earth is about 149,600,000 kilometers. So that's this distance right here. The distance from the sun to Mercury is about 57,910,000 kilometers. That's this distance right here. And you can see in the diagram that we're assuming a circular orbit for both Mercury and the Earth. Meanwhile, the elongation angle alpha is the angle formed between the line of sight from Earth to the Sun and the line of sight from Earth to Mercury. So you'd imagine that you're looking up in the sky, and you can maybe through a telescope, and you can spot Mercury, and you can spot the Sun, and you see this angle between the two. That's your 15-degree angle. So as you can see here, this creates a side-side angle setup. And you can see from the diagram that it's a side-side angle that's going to lead to two triangles. So we just need to use the law of sines to solve for two different solutions. And the solutions we're looking for here is the other side of the triangle formed, which is the distance from the Earth to Mercury. So in order to do that, I'll set up a law of sines equation using the angle side pair, sine of 15 degrees, which is the angle alpha there, divided by the distance from the Mercury to the Sun, which is 57.91 million kilometers. And I'd set that equal to the sine of m, where angle m is the angle formed right at the vertex where Mercury is located. It could be in that position, or it could be in the other position. So it'll be the sine of m divided by the side across from it, which is the distance from the sun to the earth. So that would be 149.6 million kilometers. And I'll solve this equation for m. And I'll note that when I solve it for m, I'm going to get two different solutions, one acute and one obtuse. The first solution I find, after taking the inverse sine of 149.6 times sine of 15 divided by 57.91, is 42 degrees. So that's the angle formed when Mercury is in the further position. And the other solution that I find is the supplement of that, 180 degrees minus 42 degrees, or 138 degrees. If it's unclear why the two angles have to be supplements, I find it helpful to look back at the diagram. When you look at the diagram, you can see that the triangle formed between the two possible positions of Mercury and the Sun is an equilateral triangle. And this is why it was important that we assumed circular orbits around the Sun. And because it's an equilateral triangle, that means not only are those radii congruent, but also these base angles have to be congruent. And the base angle that's closer to the Earth forms a linear pair with the angle between the Earth, Mercury, and the Sun. And because they form a linear pair, the two must be supplementary. So to finish this problem, what I need to do is I need to find two possible distances between the Earth and Mercury, two possible lengths for the third side in the triangle. In order to do that, I should first find two possible angles for the third angle in the triangle, and that's the angle whose vertex is at the Sun. So what I know is my triangle might have a 15-degree angle and a 42-degree angle, which would leave 180 minus 15 minus 42, which is 123 degrees for the angle at the Sun. Or my triangle might have a 15-degree angle, a 138-degree angle, which would leave 180 minus 15 minus 138, which would leave 27 degrees for the angle at the Sun. Now what I can finally do to finish this problem is to set up a law of sines problem all over again, where the sine of 15 degrees over the distance from the Sun to Mercury, which was 57.91 million kilometers, equal to sine of the two different angles that I have, 123 degrees over possible length from the Earth to Mercury. I'll just call it S because it's across from angle S. Or it could be sine of 27 over this S. And I try to keep using the prime notation to keep track of which is which. And from here, I can solve for two possible distances of S just by solving the two equations I set up there. When I do that, the two possible distances that I get are 187.8 million kilometers and 101.7 million kilometers. And that's how you'd set up and solve an ambiguous case of law of sines word problem.